partition function is given by zt of A here. So there is an anomaly in the system if, under a gauge transformation, the partition function is not invariant. It picks up an anomalous phase. Okay. This is not a completely invariant way of defining an anomaly because you could always add local counterterms to your system in the action that will generally change the phase, the anomalous phase. What is not trivial is if whether you can remove this phase by adding local counterterms or not. If you can't, then it's called anomaly. There's another way to think about anomalies using anomaly inflow, where we start with a classical field theory of these background gauges in a space-time of one higher dimension. Let me call that manifold n. And the classical field theory is given by classical action omega of A. Okay. And typically, this is the continuum description of what is called an SPT phase. So I'll usually call these things SPT. I'll usually call this thing SPT. Okay. And if n, the higher dimension manifold, has no boundary, then the partition function, by which I mean this phase here, is gauge invariant under the gauge transformations of the background gauge. However, when there is a boundary, when n has a boundary, it can become some term. There could be some non-trivial terms on the boundary. A simple example of this is like Chern state. And generally, or typically, it is expected that whenever you have a system with an anomaly, the anomaly can be cancelled using an SPT in one higher dimension. The way it works is as follows. We choose the higher dimension manifold to be such that its boundary is the original space manifold, and which we pick the action such that under a gauge transformation, the boundary term is exactly the opposite of the anomalous space. Okay. This way, the combination here, the original system plus the bulk theory, is gauge invariant. Okay.
So when you say classical field theory, you mean just classical function of this background field.
Yes.
And this is local in your mind.
Yeah. Yeah.
Sorry, what is omega? Omega of A.
Omega is the classical action for this background gauge field.
Thank you.
No. Yeah. So one thing we can see already is that you can shift omega itself here by a total derivative, right? Total derivative of some other functional of A. Okay, and that will just give you a local term on the boundary because it's a total derivative. On a closed manifold, it doesn't make a difference, but when you have a boundary, it just changes it just gives you a new boundary. This is essentially the local counter term that you could add to the original. So this part of the this part of omega doesn't really contribute here. So whenever you have an anomaly, you want something, some omega which is not a total derivative. That's what would contribute to a non-trivial anomaly. Okay. We could ask several questions here. Given an anomaly,
So omega is the top form?
No, I'm just using the notation. It's some classical action. Okay. We can always ask this question: given an anomaly, like a system with some anomaly, is there always a bulk SPT in one higher dimension that cancels this? I'm not going to answer this because I don't know if this is known in general. But in all the examples that I'll talk about today, it does happen. There is always a SPT that cancels it. Even if there is an SPT, is it always unique? I already talked about shifting the omega by a total derivative. So in that sense, it's not unique. But even if you remove this, can there be different non-trivial omega, which are not related by this total derivative, that cancel the same amount? This is something that I'll touch on.
Why do you call it a SPT phase?
Because so an SPT phase is like a trivial gap system. So if you ignore the symmetry, it's just like there is nothing in the system. Like the ground state agent is trivial and it's essentially nothing. But you could ask what happens when you couple it to some gauge fields, the background gauge fields, and that can reveal something non-trivial about the field. And you have an SPT phase, which is not a trivial phase. You would have this extra kind of action, for example, an action of this form in the bundle. So if this action is just trivial, that would be like a completely trivial state. But if you have a non-trivial action of this one, then it's called an SPT phase. It's not trivial.
So that for that phase, A is still with the background.
It's a value.
Sorry, Pranay, sorry. How was ZT of A defined once again? It was just the action?
ZT of A is the partition function of the theory that we started with, coupled to the background gauge with A.
Right. And then, sorry, there's just one relative sign that's confusing me. And then just go to your last equation.
Yeah.
And then, wasn't it is the relative sign, doesn't ZT of A go to acquire the additional phase e to the I integral of n omega of A, or am I wrong?
Oh no, it acquires this phase without the minus sign. Let me show that. It acquires. I use theta to denote the anomalous phase in this.
Okay.
And the shift of omega is minus theta. So that combination is gauging phase.
All right. I got it. Thank you.
Yeah.
And to be asking Abhijit's question, SPT means a bulk phase that is completely trivial, gapped and trivial.
Yeah.
And there could have been a bulk phase that was gapped but non-trivial in the sense that it had boundary degrees of freedom. We don't know. Yeah, that's what it is.
What sense FYJF is like that? Because that is the thing which is science.
Could I say so? What I'm understanding is that bulk phase is gapped. So you take this bulk theory and couple it to this E. But because it's gapped, you just get a local effective action in E. There are no other degrees of freedom at low energies because it's gapped. Neither in the bulk, which of course because it's gapped, but also because it's a trivial gap phase, also not at the bulk. Right? So the only degrees of freedom were on the boundary. Okay. And that's why you get this local effective action when you integrate it.
And then the action is action.
Classically, it's just A's are just numbers.
No, I mean the ZT of A also, even though it's a quantum theory, you could think of it as in terms of some effective action for A, right?
Yeah.
That is the different.
That is different because in general it will be some non-local function of A.
Yeah, that's what.
Because it had propagating
degrees.
Let me first give a simple example. Let me first give an example of this mechanism in the case of 1 plus 1 the compact boson. So we have already seen the Lagrange, this one here, and I'm assuming that my spacetime manifold is a torus, just for simplicity. And it has U1 momentum symmetry and a U1 winding symmetry. So the momentum symmetry acts by shifts of phi, and the winding symmetry doesn't have a local action, but we can write down the currents. Those are given by this. Okay, and for U1 global symmetry, the background gauge fields are essentially the usual one-form gauge fields, the A here. So I use A to denote the background gauge field for the momentum symmetry and A tilde for the winding symmetry. Okay. And the field phi also transforms under this gauge symmetry. So that's what we do. And the way to couple these gauge fields to the currents is by writing this, by adding this term to the action. Okay. And after global contours, we can add some local contour terms and write it in this form here. So this part is clearly gauge invariant, and this part is gauge invariant under the momentum symmetry gauge transformation, but it's not gauge invariant under the winding symmetry gauge. But we can explicitly see what happens under the gauge transformation. So when we do this, there is an extra term that depends on the gauge parameter of the winding symmetry and the field strength of the momentum. This is what signals the anomaly between these two symmetries, the momentum and winding symmetry. And it's called mixed anomaly because you can gauge either the momentum symmetry or the winding symmetry, but not both at the same time. Because of this kind of the structure. That's why it's called a mixed.
So, and maybe I asked this before, but is this the same statement or closely related or completely different from the statement that if you turn on a momentum operator and a winding operator, in general, the correlation functions are not local with respect to each other?
Yeah, I think
It's related, or is it exactly the same? Or, exactly the same.
Sorry, momentum operator, so the charge operator, momentum.
Yeah, which are bar I5. And then we try to turn on e to the power I5. And in general, there's a branch line. Because what? Winding is x left minus x right. Momentum is x left plus x right. So in general, there's a branch cut, unless you do something special, right? Compactifications, they make it, that's no branch.
yeah, if the coefficients are integers, then I don't think there are any branches.
Exactly.
But if they're
general, there's a branch.
yeah, then there is a branch.
And the set of values for which there's not branch cuts are these lattices, right? The Narayan.
Yeah.
So I was wondering the fact that you cannot turn on arbitrary momentum and winding operators freely, whether that was the same as this.
Let me discuss the SPT action that can cancel this anomaly.
Sorry, is there a way also to get alpha d tilde as the anomalous space?
Yeah. So if I didn't have this term here, then you would get the other one that you just saw. So that's like adding a local counter term, which is a new here as well. Yeah. So you can always shift which by adding local counter terms, you can shift the gauge parameter, which gauge parameter appears here. You can shift it to alpha, but you cannot get rid of this term. And so there is an SPT action in this case, which can in 2 plus 1 dimension, which can cancel this anomalous gauge transformation. And the action is given by this. It's like it's essentially like the Z and gauge theory action that I did before, except with n equal to 1. Like in the first lecture, I talked about the low energy theory of Toggenburg, which had like 2 here. Now I have just 1. But again, it's like a mutual distance sentence kind of Lagrange. Okay. And A and A tilde have their respective weights, because they are now usually U1 from gauge fields. And under a gauge transformation, this Lagrangian shifts by a total level. So when you place this theory on a closed manifold without any boundary, it's gauge invariant. But if we choose our 2 plus 1 manifold, it will be n times like a half real line, like a ring. Then there is a boundary. The boundary is just n. And on this boundary, the transformation of this SPT action cancels the transformation of the components. So this combination is then gauge invariant when we couple it to both the gauge.
N is just a solid torus, right?
Yeah. Here I chose something, but yeah, you can choose solid torus. Yeah, that also works.
That's right.
Okay. Next, I want to discuss like how this works in the exotic phi theory that I've been discussing in all these lectures.
I was sure. Sorry, here the field theory was 2 plus 1, the boundary theory is what they mentioned.
The boundary theory was 1 plus 1 compact boson.
You're trying to cancel that. Yes, now it's. So you turned on a gauge field, a mixed gauge, mixed channel term.
Yes, the work.
This
What is Lagrangian SPT? What is it? LSPT.
LSPT is this. Yes. It's the classical action of these 2 gauge fields, A and A tilde.
Thank you.
And this 1 by 2 pi is the normalization such that if you made this bulk theory a sphere, it would be nice and gauging.
Yeah. You can't put arbitrary integers, arbitrary coefficients, it wouldn't be gauge invariant.
But this is the minimum coefficient for which it's gauge invariant. It's
Yeah.
mixed.
Yeah.
With 1 gauge field, that would be 1 by 4.
Yeah, that's true.
Okay.
Okay. Next, let me discuss.
Sorry, but this is the gauge. This is in your matrix that you talked about last time. This is one minus
It's
one.
1 1. 1 1 in the off
Off
diagonal.
diagonal.
Yes.
So it has determinant one.
That's right.
Okay.
So next, let me discuss. So in that sense, the bulk theory is trivial. If you completely
Yes.
gauge it, there is no geometry.
Yes.
Any entity, right? As long as its boundary is the lowest.
No, but here the coefficient was 1. We have to cancel this signal thing, and that's why we have to choose.
Oh, no, I mean this, and the bulk manifold would be anything, right? As long as its boundary is.
As long as it's boundaries, yeah. I just chose one specific way to fill the bulk. You could choose solid orders or any other. Okay, yeah. In the 2 plus 1 D phi theory, the Lagrangian is given by this. So you may recall, like there is a standard time derivative term, but a non-standard spatial derivative term. And once again, I choose my space-time manifold to be a 2 plus 1 D torus. So time is a circle and space is also a norm. And there is a momentum subsystem symmetry where phi is shifted by a function of x plus a function of y, and these functions can be discontinuous. And we can construct the Noether currents for this momentum subsystem symmetry that are given by this. And they satisfy a conservation equation, which is not a standard conservation equation, but it's what it is. We can also construct Wien subsystem symmetry currents. They are given by derivative of this double derivative of phi in the spatial direction, single derivative of phi in the time direction, and they also satisfy a similar conservation equation. Okay. In this case, to couple the theory to background gauge fields, we need background gauge fields for which associated with subsystem symmetry, and these are the tensor gauge fields. They have this kind of a gauge transformation. The temporal component has a standard gauge transformation, but the spatial part has a double derivative. And the field phi transforms under this gauge transformation. Similarly, we can consider the tensor gauge fields for the winding subsystems. Okay. And once again, like in the compact boson, we can couple these background gauge fields to the currents in a standard way. We just write these two terms here. Okay. And after local counter terms, the Lagrangian after coupling to the gauge fields can be written in this form. So the first two terms are clearly gauge invariant under all the gauge symmetries. The second two terms, the last two terms, they are invariant under the momentum gauge symmetry, but not under the winding symmetry. So that's one choice of local counter terms. And in particular, the gauge transformation is given by this. It has a similar structure as before, as in the compact boson. Alpha delta times. This is the gauge invariant field strength of these tensor gauge fields. Okay. Now, this signals a mixed drift anomaly between the momentum and the winding subsystem symmetries in this case. And we want to construct a symmetry protected topological phase that cancels this anomaly. And in this case, it's called 2 plus 2 foliated SSPT. The first S here stands for subsystem. It's a subsystem symmetry protected topological phase. And since the phi theory was in 2 plus 1 dimensions, we go to 3 plus 1 dimensions. The bulk is 3 plus 1. And there is a very straightforward way of extending the gauge fields on the boundary to the bulk. We just add another gauge field in the bulk direction, the normal direction to the boundary, just AC. And it has a standard gauge transformation.
It's like extending the town.
Yeah.
Another town.
Exactly. Yeah. And the classical action is also very similar to what we wrote before. It's like a mutual Chern-Simons term using A tilde and A. So what we had before was A tilde times dA, where dA can be thought of as field strength of A. That's exactly the structure we have here. A tilde times the field strength of A. Okay. And the gauge transformation of this SSPT action involves a bunch of terms. They are all total derivative terms. If you put it on a closed manifold, it's gauge invariant. But if you open up a boundary in the z direction, okay, then we get this transformation here, which exactly cancels the anomalous phase in the 2 plus 1 d5.
Actually, if you could go back up once, please. Sure. The a tilde z multiplied a. This is some tangent thing.
Oh, this is the gauge and variant field strength.
That's the gauge and variant field strength.
Yeah. Under this gauge.
And so
Yeah.
You choose a tau or a z being more or a. Yeah. The z components are more analogous to time.
Yes.
So the spaces.
Yeah.
Presumably you could have done. Can you do another thing where you can take the z component to be more like the x or y?
Yeah. It wouldn't cancel the anomaly for this gauge. It would cancel the anomaly for some other gauge.
it sounds so dangerous because it's two tensor structures important for you. Yeah, you have to make like a three tensor.
X,
Many
Y,
tensors.
Z.
Okay.
I'll also give an intuition for why this case. Yeah, definitely.
So one just kind of tries and see what works.
Yeah, exactly. This seems like a small exercise, like what works, and you just write down various things and see what.
In the relativistic case, is that what constraint by descent relation?
So in the relativistic case, it's a nice question, like what determines how to extend this gauge fields into the bulk, right? That's a good question. Like, I don't know. Like in general, people assume relativistic invariance and something called some stable structure on the boundary. I don't know what exactly it means, but using those assumptions, it's kind of unique. Like the SPT is usually uniquely determined. But in these cases, like it's clear that like, there is nothing preventing you from choosing only this kind of a extension. You could potentially choose some other extensions. But we haven't looked at other extensions for this case. But yeah, you could do. This, in some sense, seems like a minimal extension, and I'll explain why that's the case.
And you had a minus sign with an a tau. That was just because times compared to a z and a tau had a minus sign.
That's right.
Is that because time was time-like or some other?
I don't. It's just to make it gauging variant on a close line. It's like the signs that you get from epsilon. 2 plus 1. Yeah.
Nice.
So one easy way to see that is if you like do integration by parts, you want to get a field strength involved with these two points. That means you should have a minus.
So this whole structure, the thing you're multiplying is anti-symmetric under tau and z interchange,
Under tau and z.
but symmetric under x and y.
Yeah.
Okay, so that's the sense in which it's a form.
Yeah. But I should add one thing though. In the case of 2 plus 1, what we wrote was a tilde dA, that was a mutual consent. But you could also write a dA. This is non-trivial. In this case, let's say you replace all these a tildes with a. It's actually a total derivative. It's not even trivial. It's not non-trivial.
Nice.
So you don't have a non-trivial pure chain, like self-Chern-Simons kind of term, using these gauge fields. So in other words, there is no analog of like chiral boson in the 2 plus 1 d5 case.
Is there a quantization of coefficients in this case?
Yes. So the coefficients here are. So if the coefficient were n and these gauge fields were dynamical, this would correspond to what is usually called an anisotropic model. It has again some excitation which are like line-ons. I talked about X-cube model in the first lecture, which are fractons and line. So if I put n here and look at the corresponding gauge theory, it would describe the low energy physics of something called an anisotropic model, which has two kinds of line-ons: electric line-ons and magnetic line. So they can move only in the z direction, but not in x or y direction. It's those kind of lines. But yeah, so this coefficient is complex.
Under the assumption that objects carry unit charge.
Yes.
And then we have the ground states, etc. That's the notice.
Yeah.
Of this theory.
Yeah.
A dynamical.
Yeah. With A dynamical, and let's say the coefficient here is n. The ground state degeneracy would be n to the 2lx plus 2ly minus 1. It doesn't depend on LZ.
Sorry, why do we have to go on lattice?
In the continuum it's infinite.
Just infinite.
Yeah, because it's Lx plus Ly, where Lx is the number of sides in the x direction. You take the continuum and that's just infinite.
And can we, sorry to slow you down, but can we roughly see that? I mean, the equations of motion from this theory will set all three field strengths to 0.
Yeah.
So you're saying there's an infinite number of
Yeah. For each x and each y.
For each.
Uh,
Stacks of theory.
Exactly. I'll talk about that now. So I called it a 2 plus 1 2-foliated SSPT. Why is that? Let's just imagine a bulk theory which has some kind of a global symmetry which couples to these kind of gauge fields. What could that symmetry be? Certainly it should be a continuous symmetry like based on the group U1. So you would have some Noether currents. And what are the Noether currents that these gauge fields could couple to? So the coupling is generally given by this. And looking at this gauge transformation, you can guess that the conservation equation should be given should be of this one. Then you can construct the conserved charges. These, like for each y, so you can integrate on the xz plane, and that gives you a conservation. So for each y, there is a conserved charge, and similarly for each x, there is a conserved charge. And in general, the structure looks like this. So let's say this is your boundary, the xy plane, x z equals 0. There was a subsystem symmetry for each x and each y on the boundary, and that extends to these leaves, to these planes in the bulk. And there are only two kinds of planes, like at constant x and constant y. There's nothing in constant z. That's why it's called a 2-foliated SSPT. You could potentially have another SSPT which also has foliation in the z direction. That would be kind of similar to what Omkar was proposing. And there could be such a theory, but we haven't analyzed. So, and here you see that you see where this large legitimacy comes. Like for each x there is a charge, and for each y there is a charge. That's why it's called a 2-foliated subsystem. We have also analyzed other theories, like lots of other theories for this anomaly mechanism. In fact, the XQ model that I talked about, that was it has this Z2 times Z2 subsystem symmetry, and you can interpret these two operators which generate these Z2 subsystem symmetries don't commute with each other. That's what gave us the large demonstrating. You can interpret that as a mixed Tufft anomaly, and you can ask like what is the bulk SSPT that cancels. There is a 4 plus 1 dimensional exotic theory, some exotic SSPT, which cancels the anomaly of the XQ theory. And we have also looked at.
I missed that. I didn't see where was the anomaly?
Oh, I didn't explain all that, but in the XQ model that I mentioned in the first lecture, there was a Z2 times Z2 subsystem.
What is X cube field theory? What's X cube?
Oh, X cube was the lattice model that I discussed in the first lecture, in the beginning of the first lecture.
Oh,
X cube refers to the low energy field theory, like the tensor gauge theory that describes the low energy physics of the X cube model.
Thank you.
Yeah, and it has a Z2 times Z2 subsystem symmetry. And these two Z2 symmetries don't commute with each other. These symmetry operators don't commute with each other. It's exactly like toric code. The low energy ZN gauge theory has two kinds of, there is a ZN times ZN one form symmetry, and these one form symmetry generators don't commute with each other. You can interpret that as an anomaly, and you can ask for a bulk SPT that cancels it. You can do the same analysis for the XQ theory. And we have done that. Okay. Similarly, there is a more interesting example. Which is a 1 plus 1 theory based on a compact scalar. It's not the usual compact boson. It has a ZN subsystem symmetry, just a single ZN subsystem symmetry. It's actually very much related to the 1 plus 1 Euclid boson. So something like delta phi, del x phi, something like that. And we have constructed two bulk SSPTs which cancel the anomaly of this theory. So the ZN subsystem symmetry has an anomaly, and we have constructed two bulk SSPTs which cancel the anomaly. One of them is 1-foliated, which seems like the minimal thing that you could do. So the subsystem symmetry acts at every x at every point. And the bulk SSP, in the bulk, you just extend these points to a line. The symmetry acts on these lines. And the other SSPD, which is a two-foliated one, has these lines in addition to these lines. So there are also foliations in the other direction. Okay. They don't immediately act on the boundary, but you could have such a bulk SSPD which cancels the anomaly in the boundary. So this shows that you need not have a unique SSPD that cancels the boundary, the anomaly on the boundary. So if you want to uniquely specify it, you have to give some more information, like what kind of structure you want to present. In the ordinary theories, I think like it's implicitly assume that you want to maintain relativistic invariance and stuff like that. I don't know what other conditions are imposed, but usually seems like there is a unique SPD. But in these cases, it's not clear what structure you want to preserve. You could say that you want to preserve only the minimal foliation possible, as minimal as possible. So that would choose this SSPD here. But you could also like allow for more complicated foliation structures, in which case you have more possibilities. That's all I wanted to know.
It's anybody in the Zoom audience have questions? I guess not. So anybody in the audience here?
So in the first lecture, when you said the anomalies could be cancelled on the lattice,
Yeah.
you meant sort of with the bulk lattice.
Yes.
I see.
Yeah.
So I thought you could laticize your theory in the same dimension and cancel it.
No.
That, of course. Okay.
So all I did was like the anomalous gaze transformation. Like we see here. Here, this transformation, you could see that even on the lattice. This kind of gaze. You could on the lattice, we can write down the modified Villen form of this Lagrange. Okay, and couple it to gauge fields. Essentially in the same way, except there are other integer gauge fields that you have to add. And then you could ask like whether this Lagrange is gauging it or not, and you would get terms like this.
I see.
And then you can add a bulk action which cancels this SPT action. Yes, you can do everything on the lattice.
Yes.
Nice modified Villen form.
And perhaps also something I had misunderstood that. The reasons for many.
Yeah.
Is there something to be said about corners?
Yeah. So far I opened the boundary only in the one direction.
Yeah.
But if you open it in like two directions, let's say you have some kind of a quadrant. You could have some corner modes. We haven't analyzed that, but we are not sure like what the boundary theory would be in that case. So yeah.
Because it has that structure, like
Yeah, exactly. You could also have
naturally seems like you open that up and then there's something like
That's right.
it has some weird type of anomaly which is cancelled by two high dimension.
Yeah. So yeah, we tried. We thought about it, but this seemed like the cleanest thing to say for now. The convert mode is kind of tricky. We don't know what the boundary theory would be in that case. That's why we're not talking.
It would be nice to understand, if you start with some normal quantity theory, what are the assumptions that you relax? So to get to this kind of structure, right? I mean, one is that you immediately relax Lorentz invariance.
Yes.
So that is sudden relaxation, right?
Yeah.
A big. That's right. It would be nice to do it in some tight framework. See whether these features, some of these interesting UVIR features are there. Well, this is a broad comment.
Yeah.
Some interesting features are there in a more tightly constrained theory, so that one understand it gets to those features.
Yeah. So there is one example which is in between these two. Like in the subsystem case, you need all these foliation structures, so rotation is completely different. But if you are willing to give up boosts, and still want to retain spatial rotational symmetry, you could have these kind of dipole theories. where instead of a conserved charge for each x and each y, you just conserve the total charge and the dipole moment. So there you can still maintain rotational invariance. But the theory still has interesting UVI mixing kind of phenomena.
Can you write down this theory?
Yeah. Yeah, for example, if can have this plus the x square phi whole square. Or in higher dimension, you can replace this with Laplacian. So then you can easily preserve the rotational invariance. But this theory has infinite Gramsci degree. While the subsystem thing didn't have infinite Gramsci. The 2 plus 1 theory doesn't have infinite Gramsci degree, but this one does. And that comes about because you can shift phi by some linear function, something like this. When you place it on a spatial circle, you can shift phi by this, and these kind of shifts are not suppressed by the action. This is the action is invariant under this. So this is a symmetry. But phi is a compact scalar. You can also wind in the extent, the spatial direction. So whenever you shift it by this amount, like the shift it by a configuration of this one, it changes the winding charge of the winding number of phi. So the winding symmetry and this dipole symmetry, they don't commute with each other. That leads to infinite Gramsci. So yeah, you could have you could still have rotational invariance and have all these features.
Also, this theorem, like Riech-Leiter theorem, etc., they work in these string theories. This Riech-Leiter theorem. There's some general theorems about some ground states in quantum field theory. There is some statement about analyticity of correlation functions.
Presumably they assume everything. I don't know.
I think it's assumed.
Maybe there's some. Any problem with theories with background gravitational fields or some other gravitational knowledge?
Yeah, so I don't think you can couple it to an arbitrary manifold because you need foliation structure at least for the 2 plus 1 theory. But if you have a foliated manifold, people have defined some kind of metric on foliated manifolds, like manifolds with foliation structure. And you can place these theories on such manifolds. And people have studied these things.
Yeah. So this foliation structure is not, I mean, here it was kind of rigid because it was X and
Yeah.
Y.
Yeah.
But you're saying you can also.
You can deform it a bit.
Okay.
As long as you have some kind of foliation structure, you can place this theory.
So, what exactly is the foliation structure? Being able to write a metric in certain way?
Not the metric. It's like you should be able to divide your space. Let's say you have a 2D space.
Yeah.
You should be able to divide it into a set of lines. Like the entire space is divided into a set of lines in one direction and in the other direction, 2 directions. Similarly, in 3 dimensions,
So without these lines shrinking.
Yeah.
This is an additional structure.
It's an
Anything
additional
can
structure.
admit this, right?
Huh?
General thing would admit such a.
No. For example, on a sphere, you can't do this
I see.
because those lines
I see.
would meet at this point.
Because what?
They would meet at the poles. Right?
Ah.
You can't have separate lines. On a torus, you can always do this in any dimension.
Or you could have lines like this, but then they would shrink.
They would shrink. Yeah.
They're like the equator, the latitudes. They would shrink.
Yeah, but that would be just one foliation. So if your theory requires only one foliation, then you can do
Or
that.
could you do latitudes in the other direction?
Yeah, but as you said, the problem is they shrink to a point. Yeah.
Very well.
I don't know if this is related.
So is the continuum path, when you write down your continuum theories, is the continuum path integral sort of well defined? In the sense that you're allowing, sounded like you were allowing quite jaggedy configurations.
Yeah. Yeah.
So do you know what kind of configurations you're allowing and what it
Yeah. So they Napi and Shuri, they analyze this quite carefully. So as I mentioned, the energies of the momentum and winding modes I said was like 1 over LA kind of. The energies of the plane waves that we just made here was equal like usual standard. But for the momentum and winding modes, they scale as 1 over A, 1 over A. But a typical lattice configuration on a lattice would have an energy which scales as 1 over A squared. So, which is parametrically larger than the momentum and winding modes. So, in that sense, you can still differentiate between the momentum modes, these minimal energy charge states, and a generic state configuration on the lattice. So, there is a sense in which you can separate them and you can still talk about it. If you are a conservative person, you could just ignore these states. These are just infinite energy and you wouldn't deal with them. These are the only states in your field. But you can be ambitious and you can still deal with these precisely. And this is made more precise by going to the modified Wilhelm formulation on the lattice. Right? So there everything is finite, you can talk about anything.
Suppose we were just directly look at it.
Yeah. Then you have to like
These ones are not there.
yeah, these are not there.
And again, you mentioned this before, I think, but so far the continuum theories you talked about were sort of free theories. Now, and if you add interactions consistent with the subsystem symmetries, they're all irrelevant.
That is an interesting question. I don't know the answer. But, so in all the cases that I discussed, the symmetry is realized non-linearly. It's like a shift symmetry. So there are ways to write down like a Lagrangian where these symmetries are realized linearly, but you can't do it with a quadratic action. You always need a action involving like 4, 5 or something like that. Yeah, if you want to maintain all these symmetries. So that's already interacting. Like just if you want to realize the symmetry linear. But yeah, I don't know much about these theories. Yeah, but recently there has been some work on this kind of actions with quartic kind of interactions, where instead of having just one scalar, you have like n scalars, and then you do some kind of large analysis on this. And there people have made some progress and like, discuss the phase diagram of the theory. But I don't completely understand, but people have studied that in the large end. That would be like first example of interacting front.
I see. But just like forgetting about large and just perturbation theory around this. There's no simple example.
Yeah.
Yeah.
I also wanted to mention just one thing that I didn't mention all this time. Like these global symmetries, the U1 momentum and winding subsystem, I keep talking about them as if they are internal symmetries. But they don't actually commute with the translation or rotation, the Z4 rotation. Right? Because when I translated the charge here goes to a charge here, they're not the same charge. It seems to break the Coulomb modulity. So you can think of these as like examples of counter examples to Coulomb modulity. That's another thing about these theories. There is no real delineation between internal symmetries and space. They all don't compete with each other. They're all mixed concepts.
In interaction, interacting the one would have to talk about RG flows and such. And you were saying that these bits are talking about RG flows.
Yeah. Because at a given energy, it's not like you have some finite number of states with that energy. You have infinitely many states. And the contour is not even like a compact, it's non-compact. So people still try to do something, but I don't know. I don't completely understand how this works. The easiest thing to do would be just put an infrared regulator, IR regulator, like for example, like how in the correlation function, whenever we have UV divergence, we just put IR regulator in it, regularizes things. So once you put that, then there are not too many low energy states. There, presumably, you can do something, and then you can try to take the limit continuing. But I don't know exactly how to do this.
Any other questions?
So, given that there is this foliation structure, this model, I guess the entanglement entropy would depend on the shape also, right?
Yeah, yeah. So I
Not
think
just on the area.
yeah, I think when people compute the entanglement method in this series, they take the region to like according to the foliation structure. Like for example, with some finite entity of x but all one, and or a box. They don't just take some arbitrary shape. The shape has to conform to the foliation structure. Then it's easy to compare.
There are no further questions. Let's